In dependency parsing, what we want to do is uh, we have an input, a text piece, maybe a sentence as input, and then we want to see how the different words they relate with each other. Okay. When we talked about constituency parsing, what we did is that we tried to see how the different individual phrases they connect with each other to uh, to give rise to larger phrases. So it was mostly about the constructs of the phrases. But here we are actually looking into the relationship of the different uh, between the different words or in the input sentence. So this is the one. Dependency grammar. So if you look at syntactic structure of a sentence, that can be described in terms of the words in a sentence or set of directed binary grammatical relations that hold among the words. So let us look at this example first. I preferred the morning flight through Denver. So this example is there from the book. So here it says that the flight, the word flight is a noun. Okay, it doesn't say that it's a noun. If we look at the word flight, now when we read the sentence, we know that morning is actually a modifier. It is restricting the scope of the flights, or it is in some sense, it is describing when the flight is departing, right? So morning is very closely associated with flight. So here we have an edge from flight to morning. So this one will be a head word for this relation, and this one will be a dependent. Okay, so this will be a head word, and this will be a dependent. So now let us look at something else, the and the word flight. So the word the is an article, and here this article is corresponding to the word flight. So when we say the, it's actually referring to the flight actually. So it is a determiner for the flight. So again, head word, the main word is the flight, and the is the dependent word. Now there are many such examples here. So we'll look at that. We'll look at the different labels and so on. But to give you an overview of what is dependency structure, what is dependency parsing, what is dependency grammar, I think we can. So this is the core thing at the. So this is the thing at the core of that explanation is that the different words in a sentence, if we look at them, we'll see that the words relate with each other. Now this dependency grammar is trying to capture that interconnects the dependency between the words, and if we get these interconnects, essentially we get a structure of the sentence, right? So this structure is the dependency parse of the sentence. So this is definitely a structure of the sentence, and here we have the words in a sentence and a set of directed binary grammatical relations. Okay, so these are all directed relations, and well, uh, when we say binary, so each edge actually has a label. Now, if you look at a given level between a pair of nodes, that level either exists or not exists, does not exist. So essentially, it captures relations, grammatical relations among the words. And relations among the words are expressed with directed and labeled arcs, same as this one. And root denotes the head of the entire structure. So root is the head of the entire structure, and the verb typically will be the root of the dependency structure. So all other edges, if you see, the edge will start at some word and end at some word. So the starting part will be called head, and the ending part will be called the dependence. But in case of the root, right, there is no parent. So the thing that we see in any tree data structure, the root does not have any parent. Here also it's the same thing, that we have a root which will denote the head of the entire structure, and yeah, so this root word will not have any dependency on any other word, so that's why it's a root. Okay, so any questions till this point? Fine. So this is where the dependency difference lies with the constituency parsing. So here, all these relations, right? Prefer and flight, then flight and Denver. So they can be distant from each other, and this distance can be anything. So here in between them there is one word. So for prefer and flight there is an edge, but the distance among them is two words, and so on. On the other hand, constituency parsing, since there we are talking about the phrase construction, so the words which are next to each other, the words which are adjacent, they get merged. So that's why we looked at in the CNF grammar also, no? So A to B, C. So B is one phrase or unit. C is also one phrase or one unit, and they are getting attached. B and C are next to each other. But here it's not needed. So that's why we can also see that if there is some information which are in the sentence slightly far away, that kind of information can also be very easily obtained from this. Okay, now this is about what we mean by the dependency structure. So let us move on. So this is the phrase structure analogy. For the same tree, if we get the constituency parts, we'll get this. So morning and flight, they're getting attached, and then through and inward, they're getting attached. And morning and inward, the first connection that we are seeing is here, but that also involves some other words in between. Okay, so this is also called the typed dependency structure because all the edges, they have some type. Now, what are the edge labels that are allowed? Again, different data sets allow different labels, and yeah, so and the number of labels and names of labels, those vary from dataset to dataset. I believe in this presentation I do not have the links or mentions of the datasets for this. When I upload the slides finally, I'll add those things as well. Okay, so fine. Let me also see if I can show you some examples of dependency grammar.
Hi, sir. Good morning. Is it possible to upload the slides, sir?
I'll upload.
We
I
just want
think.
to annotate on the slides instead of writing everything else.
Sorry, say again.
I just wanted to annotate on the slides instead of writing separately. That's why I'm just asking.
Mm, okay.
Thank you,
Fine. So
sir.
I can do that. Actually, after the class, I do certain modifications to the slide and upload the final versions. But if sharing at this point helps, I'll do that. So let's go through the examples and then I'll share. So
Yeah,
let
thank you, sir.
me. hmm, Okay, let us think about a sentence. So Or maybe we'll start with a short sentence and then we'll go to a longer sentence. So the temperature is increasing. Let us see. So we'll just have this thing. Well, so this is simple. The parts of speech we can see named entity. There is no named entities. Dependencies, right? So is huh? is a verb, and then what is increasing? The temperature is increasing, right? So there is an edge here, and the is a determiner for this noun. So this is the thing, and for increasing, actually increasing is actually the root here, and is is an auxiliary verb. So this is one thing. And right now this is basic dependency, then enhanced plus dependencies. So another set of labels will be allowed inside this. So for this simple sentence, I believe all the labels are fine and matching between these two. However, for some other sentences, this may be are different. Let us look at another. mm,
Sir, how do we find which one will be the root?
the main verb will be the root. Okay? The verb will be the root.
Okay.
Okay, so let me see here. The temperature is increasing. So here, increasing is the verb, is auxiliary, and the temperature is the subject to that. The temperature also, has a relation. Temperature and the that together was the subject, but there also, you have a temperature and there is a relation between them. And what you see is that here determiner, noun, and subject. This is NUM. Uh, okay, not very sure what this means. So the labels are actually getting different because this RNNLP may be using a different sets of dependency labels as opposed to the core NLP. And yeah, again, they also have their APIs, and the outputs can be there in different forms. Uh, okay, now let us look at a larger sentence and see how the parliament, okay, session was interrupted again multiple times. Or the entire thing may not be visible on the screen if it is very long and needed to be adjusted. Okay, let us see. Then submit. Part of speech, NER. Okay. Now also, so can you tell me what will be the root for this? Okay, now this is a little tricky because here we have and to join two things which could be related, and essentially we have two verbs, right? Need to be adjourned to be, and there also we have interrupted. But this is the main clause here, and this becomes an auxiliary, subordinate clause. So here the root again will be this one. Yeah, right. So this is the root interrupted, and then there are different relations. So subject is the parliament session, and there also you have yeah, parliament, it'd be nice to see it in a tree format, but somehow possibly this one does not allow that. Okay, now there is one more.
Sir, why is interrupted the root?
That's part of the main clause.
What do you mean by main clause?
So in English, the clausal structure is there, right? So there will be a primary clause and there will be some subordinate clause and so on. So the subject and so yeah, the parliament. What was the sentence? Session was interrupted again today and needed to be adjourned. So this is getting attached to this main thing. So this is the main clause, and these attachments will be. So in English we have this clausal structure, right? So this will be a subordinate. That one.
So, sir, main clause had 7 tokens. Why is interrupted the root?
So interrupted is the verb, right?
Yes. So, verb is always the root.
Yes.
And what if there are 2 verbs in the main clause?
Then I believe it will be the now if it is connected with and or something. Say the people were singing and dancing. So we need to see
Mhm.
which one is favored by the algorithm. But otherwise, if so where they are parallel actually. In that case, need to see what the algorithm, how the models are fetching that. Otherwise, single verb, straightforward, that will be the clause. That will be the root.
Okay, okay.
So here also from these verbs, so many different arcs are emanating. So interrupted to was, and from here to parliament session again. So some temporal information is coming here. It becomes adverb. Today again, it's some kind of adverb because we are talking about time, and so on. So basically, the bottom line is uh, words, how they relate with each other, and the most important thing here is the verb, because anyways we know that typically in English the verb will all needs to be there except a few uh, except a few specific cases, and all other words actually describe what is happening with the verb, what is happening, which is the action which is reported by the verb, who is doing it, how it is being done, and things like that. So when we talk about semantic role labeling, this will become a little more clearer. So that's what those kind of dependencies the methods will try to capture. Okay,
Sir,
now
what if there is no verb in the sentence?
let's see what happens. Give an example.
Uh, Qutub Minar is in New Delhi.
There is a verb is, right?
Okay, but that's a helping verb, right? That's also
That's a verb nonetheless.
okay, okay. Then I'll have to think.
See, in short conversations, there can be like hi, hello. And these are greetings. There are no good morning. There are no verbs there.
Mm, yeah.
So right. So these kind of examples will be there as corner
What,
cases.
sir? What if it is like what a beautiful flower? Things like that.
The entire thing will be marked as noun. Sorry, no. So here the noun is being taken as the yeah, as the root.
These rules seem to be very like subjective sort of things. There is no one. I mean, is there like a set pattern or a heuristics the way you can determine these things, or it varies from algorithm to algorithm?
See, when we look at the ground truth generation, algorithms may vary depending on how they're doing it, what features, what predictions they do. But verbs will, the way the things will be annotated, if you look at majority of English sentences that you pick from any reasonable resource, will have the verbs present there. So that way it is, that way if you look at a large collection and over that what kind of relations exist, so the roots will be, the verbs will be assigned as the roots. In fact, if you look at the data sets also, there also people would have annotated like that only.
Yeah, I mean, like I understand the root, but the way they build the trees or the this dependency parsing within Spacey and Allen also, there might be like differences in the way they are building it.
Yeah, there may be differences. See, whenever they build their, they'll have their own model and they'll evaluate it on certain data sets, and then they will, uh, yeah, and then they will release it or package it or whatever. And and when we talk about the data sets, the labels will be defined there, the examples will be defined there, and depending on the algorithms, the things may vary. Say, for example, to give a very simple example, suppose for some of the annotations that okay, if there is the root, what is the subject or something. So either somebody may use some rule-based technique, somebody may use a name-based classifier, somebody may use a deep learning-based things. The predictions may vary, and that's what we will see in the output. Yeah, and
Okay.
yeah, in natural language there will be subjectivities, but in most of these scenarios, if the grammatical structure is proper, we expect to see some agreement. Yeah, if there are no ambiguities.
Okay. Okay.
Okay, let me. mm, Okay, so mm, okay, I guess Chaitanya asked for the slides. Let me see how to share it now. Okay, I guess I was muted. So Dependency relations, they describe the role that the dependent plays with respect to its head, and there could be different kinds of relations like clausal relations, nominal relations, modified relations, and so on. So clausal relations actually describe the syntactic roles. I mean, they are more towards the syntactic role, right? If there is a verb, so there will be a subject, there is a predicate, object. So those things, those structural things will be listed using the clausal relations. So nominal subject, a direct object, complement, and so on. So some of the levels are such that you need to have a very strong grasp on the English grammar and so on. However, there are quite a few which are somewhat easier to understand. So for example, a nominal modifier. So sometimes the adjectives they are used to modify. Sometimes there are adverbs which are there to modify to certain words. So nominal modifier will be there. Then adjective modifier will be there. Numeric modifiers could be there, like 3 vehicles and so on. And then a determiner will be there, prepositions. So all these could be conjunctions could be there, and or. uh, so these could be some examples of relations. Now, if you look at the actual sets of relations which are there in different data sets, there are data sets where 40 plus relations are also there. Now, again, one example, United canceled the morning flights to Houston. So here there are some clausal relations like in subject and D object. So cancelled is the root. Who cancelled? The subject is United, and cancelled what? The flights. So this becomes the object. Okay. They identify the subject and direct object, and then there could be like in mod like morning flights. So this is again restricting the or explaining which flights. So that specific thing is in mod. Then there could be case relation, like this is coming from preposition. So case will be for prepositions, and yeah, flights to Houston. Again, this is another modifier, and so on. So what are the benefits that we get from dependency grammar? So it abstracts away from the word order information. So if we so the edges, right? So edges can actually go far apart. So word order relation information will go away. And also suppose if we talk about say the same thing in active voice and passive voice, the sentence structure will change. But hopefully the dependency grammar, the same kind of relations we'll be seeing from both the sentences. And if we look at constituency parsing, so CFG again, they try to attach together words or phrases which are consecutive. So position or place is important and so on. So this is another thing. So I gave the example of active and passive voice. So in English, still the language order and the word order is kind of, if I can say, rigid. The same sentence may not be written in too many possible ways without introducing many new words or dropping many new words, many words. Uh, yes, but in several other languages, things can be the languages are morphologically rich. So there is a word to which we can attach certain prefixes, suffixes, and so on. And the moment we do it, the same sentence we can possibly write in multiple different ways. And when we say multiple, it can be 4 or 5 different ways. They mean the same thing, but if you look at the words, their positions, and there could be lots of differences among them. Now, when we talk about dependency grammar, so there could be a way of normalizing or understanding a common structure for all those different versions of the sentences. So it is quite helpful. It has been observed to be quite helpful for different languages. And yeah, so what it also means is that the dep the algorithms that find the dependency grammar for these kinds of sentences, they also need to be very robust to be able to identify those kinds of structures. So for English, we have a lot of resources, so we can build uh, many algorithms. Challenge for other languages is that we may not have sufficiently large data which is annotated for training this. So again, this is has been a very active field for NLP research, where people try to come up with language-specific dependency parsers, and they use different kinds of signals from the basic linguistic perspective also. Then head and dependent relations, they provide an approximate semantic relationship. So in some cases, we saw that syntax is getting represented, but it also gives you a semantic relationship. So the semantic would be useful for co-reference resolution, question answering, and information extraction, right? So if you look at the different labels in the previous examples, it's very clear that if you have the proper annotations of the labels, they could be helpful directly, sometimes indirectly, for question answering, information extraction, and so on. Okay, so a dependency tree, it will be actually a directed graph, V comma A. So V is the set of words in a given sentence. In many cases, the punctuations are also considered to be nodes in the tree. So V is the set of nodes, and A is the sets of arcs that capture the head and dependent relation. So some properties, what are some properties of the dependency tree? It will be connected. So you all know what is the meaning of a connected and disconnected tree or graph. Graph. So this one will be a tree. It will be connected, and there is single designated root node that has no incoming arc. So here this is the root, here this is the root, and each vertex has exactly one incoming arc except the root. And so root has no incoming arc, but everything else will have uh, an incoming edge. And there is a unique path from the root to each vertex. From the root to each vertex, you'll see an unique path. You can verify this from the diagrams. Okay, so I guess that part is done. And there is something called projectivity and non-projectivity. So if you look at the left-hand side figure, you see that the edges are not crossing. On the right-hand side, you see that the edges are actually crossing. So dependency is projective. It can be drawn with no crossing edges, and otherwise it becomes non-projective trees. So there are non-projective trees, actually they arise in languages where the word order is flexible. So then, if the word order is flexible, it can change. Then there is a chance that we'll see crossing edges. So there are many algorithms that people develop, which are for projective trees. There are algorithms which are there for where people try to say that, okay, my algorithm will work for non-projective case also. So yeah, sometimes the algorithms also differ. If you look into those algorithms, you'll see. Yeah. So this is about projectivity, and there are some properties of the dependency tree.
Sir, in the second sentence, how is was the end mod here?
So the main verb is cancelled, right? And which was already late. Now, which was already late is actually describing the flight, right? So
Yeah,
that's why this becomes a part of the modifier.
but like which is a case because it's a preposition,
Mhm.
and like rest of the this clause has been broken down, but I couldn't get like why exactly is it saying that this entire clause is the modifier, or is it saying that was is the modifier?
So no, here if you talk about this edge, this is the label for this edge will be modified, and this label is assigned with that edge which is connecting only one single word. Now, if you try to see the structure in a tree-like fashion, so from flight there is this word was. Then one level down, you'll have which. On the other side, one level down, you have late and then already. So in some sense, this entire thing, this part, this entire thing which is actually describing the flight will be rooted. That subtree will be rooted at was. So, and that one, the label is nmod.
Okay, sir.
Now we'll talk about one simple technique, not so simple, but yeah, one traditional traffic technique for dependency parsing. And this is, we can call it as a technique. We can also call it as a framework. It has certain components where you can replace the things from one algorithm to another algorithm, and you may get different results. So we'll talk about the transition-based framework for dependency parsing. Now, this kind of techniques are often used quite successfully in case of compiler, and this technique is actually motivated from there. It is based on shift reduce parsing, where we look at the tokens in the input, and every time we make a decision like shift or reduce, and after that, and this is the process that we do, and we keep on doing this, and finally there is a goal state that we reach, and we say that okay, we are done. So let us see how it works. So here, this is the parser, okay, which will make the decisions regarding shift reduce or some other associated decisions. There's an input buffer from which the words will be consumed, or the tokens will be consumed rather, and it also maintains a stack. So every time the parser will read or fetch something from the input buffer, make some decisions, and it may, or it will rather, uh, it will require it to make some modifications to the stack, and the stack will have some initial configuration and some goal state configuration. So initially it contains the root node, something as root, and then in the end we'll have the stack as empty, or some special end marker will be there. So that's the initial configuration. Stack contains the root node, and the word list or the input buffer is initialized with the set of words. Not only set, it's the sequence of words. Goal configuration, empty stack and empty word list. So if the input buffer is emptied, it's blank. That means all the words we have consumed, but the stack is not yet empty. That means certain other operations need to be done. We'll do those operations, and then finally this goal state will be reached. Now sets of relations will represent the final parse. So it can output the dependency relations and the final parse. Okay, so we said that the parser will take some action depending on what is there in the input buffer, what is there into the stack, and what are those actions. So in this case, the actions are left arc, so it may establish a left arc, a right arc, it may establish a right arc, and otherwise it can simply shift. So these are the three possible actions defined here. So left arc means head dependent relation between top and top minus one. So this is the stack top. This is, let's say, stack top minus one. Left arc means top to top minus one. There will be an edge, right? So the top to top minus one, since it's a stack, right? Top minus one is entered before, then top was entered, and yeah. So this one came first, and then this one came. So say for example, right. So that means the edge is going from right to left. Since this one came later, this one came after in the sequence. So we're going from right to left. So it's a left arc. And right arc means head dependent relationship between top minus one and top. So from here to here, the edge will be there, arc will be there. So it will be a right arc. And after doing this, we remove the top from the stack. And shift means we'll remove the word from the input buffer and directly put it at stack top, will not do anything else. Okay. So, this entire thing, a very high level outline could be something like this. Function dependency parse, input is words, that is the sequence. It will return the dependency tree. So the state will be three things. Root will be the configuration of the stack. Sequence of words will be the configuration of the buffer. And this blank will be the sets of dependency relations. So initially we don't have any sets of dependency relations. So this will be the initial configuration. And while the state is not final, T oracle state. So let us call this parser as an oracle. So it will take this thing as input, return the action, and will apply the action on the state. That means on this. So it may mean modifying the stack. Of course, we'll be taking one. Well, we may or may not take something from the input buffer, and if needed, if some edges are created, that edge will be, these edges will be added to the dependency relations. So that it will operate the action on this entire state. And yeah, finally, when the state becomes final, we'll return this thing. So it's an example. So stack initially has only the root, and this word list is the complete thing, which is book me the morning flight. And suppose the oracle, it says I should do shift now. Then the first word that we are currently pointing at, that goes to the stack. So stack had root, we have added book, and here we have the remaining things. Okay. Now, again, based on this stack, based on this word list, the next action recommended by the oracle is shift. So we'll do the same thing. Me will go to the stack and will be eliminated from the, will be removed from the word list. Now, given the stack, given the word list, the next action is write arc. So that's what the oracle has suggested. So write arc means what? Write arc means the edge will be from left to right or top -1 to top. So book to me is the relation that we get. Okay, and we are not moving anything from the word list. Yeah, but we remove top in case of write arc. Write arc, remove top from stack. That means me goes away, the stack gets modified. So then this is the part of the input, this is the part of the word list as input, and now the next action is shift. So the goes here. The next time also action is shift. So morning goes here. Next time also this is shift. So flight goes here. Now you see that the word list is empty, but still the algorithm will not terminate because stack has not reached the goal state. So now based on this word list, based on the stack, the method, the oracle suggests that left arc should be the thing. Left arc means it will be from top to top -1, or that is flight to morning. So this one is there. Similarly, the next of the rest of the sequences will be taken care of, and we will have finally something called root only remaining in the stack. So at that point we are done. So then the algorithm can terminate, and this will be the relations. Now these relations, if you stitch together in the appropriate form, this is the tree that you will get. Now, okay, I should not say that this is the tree that we get. This structure you will get, but these labels will not be present because here we have not done anything with the labels, edge labels, right? So there are algorithms. So again, there are algorithms that can assign these labels. But if you only look at the head and dependent structure, the trees, the edges, unlabeled edges, this is the structure that you will get from this operation. So again, although the working is simple, the main thing is how do you predict this action? How do you decide these actions? So people actually make machine learning algorithms to predict these kinds of actions. So let me, okay. Okay, so let us talk about the algorithm a little bit more critically. So are the sequence of actions unique? The answer is no. There may be more than one path that leads to the same result. There can be more than one sequences of operations that leads to the same result. And then there may be other transitions that lead to different equally valid parses due to ambiguity. So when we talked about constituency parsing, there also we saw, right? Same sentence, there can be different valid parses of that. So different valid constituent parsing will also indicate that there is some ambiguity or some different interpretations that could be possible for the sentences. And if the sentences have different interpretations, the roles that the words play in each of those interpretations, they can also vary, or they will also vary. So that's why here also, if the sentence is ambiguous, there can be multiple equally valid parses. Or even if they're not equally valid, there can be, one parse could be more meaningful, more suitable, the other one may not be. But so all of them could be, there can be multiple valid parses. So that's one thing. And the second thing was like how to generate the labels for the arcs. So here again, one suggestion that was given is that when the oracle predicts the label like left arc, right arc, instead of that, let it predict left arc, then the label, right arc, then the label. So yeah, and then you'll get that labeled tree directly. Job of oracle will be to return the correct action from a large set of actions. So of course, if it is shift, left arc, and right arc, we will have only three labels. So if you think that predict the next action to be performed as a classification task, so there you are working with only three classes. But here with each arc, if you want the label also to be given, then the total number of actions become 2n plus 1, where n is the number of labels. So the set of actions become large. And then is the oracle always right? So oracle is nothing but a machine learning algorithm. And if we expect that if it is trained based on a large number of examples of covering various types, then the oracle will be actually be able to learn from that. But as it happens with all machine learning algorithms, will not be able to say that it's working correct every time. So oracle is not always right. And yes, so we don't expect oracle to be right every time in practice. So machine learning methods are used and have been used. And although, so as I mentioned, the shift reduce can be considered to be a framework, and the oracle is nothing but a classifier. And if you have modify your data set, if you modify your classification algorithm, you will get different results. So there is a lot of scope to modify or get different results by modifying the algorithms for doing the action prediction. So this is one approach that was proposed in using deep learning techniques. So at each and every point, the transition we are deciding, right? Shift, left, right, or we can also have the class level associated transitions. So each transition is actually scored using an MLP. So this is an MLP that predicts the score for left arc, right arc, and shift. This can be probabilities also, and the best action can be picked greedily. So the question is, what would be the inputs to this MLP? So here, different possibilities exist, and this is what these people proposed in this paper. So what they said is that you take the input, okay? The brown fox jumped over the lazy dog, and in the end, you also add something called root. So that's what they said, because that root should be there in the stack. So it's also a valid token from the stack's perspective. And then for each of the things, you get the initial embeddings from some source, and then you pass it through, say, by LSTM. So the output that we get from the by LSTM will be, so yeah, they have shown both the LSTMs separately here, forward and backward, and their representations can be concatenated to get the representation for each of the inputs, right? So this is the by LSTM representation for this is the by LSTM representation for brown, and so on. And then they look at the current configuration of the stack. In the current configuration, suppose we have the jumped over in the stack, and yeah, S0, S1, S2, and then the current word that we are looking at is the, right? So based on the current word, based on the stack, we need to predict the action. So this current word's representation comes as an input, and last three from the stack they take. So over, jumped, and the. So these three things will also come to the MLP as input. Based on these, the MLP does the prediction, and we decide which one to take. So this is one of the earliest neural network based approaches for transition based parsing. Then on, there have been quite a few other approaches also for this task. Any question? Okay, so then we'll talk about one more algorithm. Now the next algorithm, it's not great, definitely not one of my favorites, or you'll be able to see a lot of drawbacks or issues with this approach when we discuss that. But still, this is slightly different from the other lines of approaches. So here, actually, the different ages are scored. So here we are scoring the actions, right? So here different ages are actually scored, and those ages which have high score, they are combined together to give the tree. So newer kind of thought. That's what I thought of, or different kind of thought. That's what I thought of, having it in the slides for discussion. So the basic idea is that each possible dependency arc is scored using an MLP, and that is fed the bias element of the words at the arc's endpoints. So let us see. We're trying to at the brown fox jumped, and then we have it is this extra, I guess, is the stacks thing, and so fox to brown, there is a possible edge, right? Now fox to brown, we need to find a score for this one. How do we do that? We get the representation of fox coming out from this by LSTM. We get the representation brown coming from this by LSTM. So for this red edge, we'll get brown's representation and fox representation. Then fox to this blue edge, to get the weight for that, we'll get the representation of we'll get the representation of fox. Okay, so this again goes through an MLP, and this gives a score. Then for this green edge, fox and jumped. For fox, we get the score. For jumped, we get the score. Pass it through MLP to get, sorry, not score, representation. And after passing it through the MLP, we get a score. Similarly for this one. And then we sum up all the scores. Now for the sets of edges for which the score is maximum, that can be picked. So that's what it said. Each dependency arc is scored using an MLP, and this MLP is fed what? The bi-LSTM encodings of the words at the arc's endpoints. This arc has two endpoints, and these are their representations. Right? Now, individual arc scores are summed to produce the final score. So all these individual arc scores, they are summed to produce the final score. Now, when parsing, compute the scores for all possible order n square arcs and find the best scoring tree. So definitely, it's not a very technique. You are actually trying to look at that entire search space, and then you are trying to look at the best possible tree. And yeah, so but still, that's one approach that people can think of, people can modify suitably to have some interesting algorithm. And here also, as you can see, the edges, we're looking at the edges, but the edge labeling, how do we do the edge labeling? One can use another classifier for doing the for assigning the labels. Okay, any questions? Okay, now so far we talked about the things like what is meant by dependency parsing. We looked at how does a dependency tree looks like, what all information does it give. We looked at some demo. We then tried to look at a few algorithms. There is an algorithm framework for shift reduce parsing that we looked at. Then we looked at a couple of individual algorithms for predicting the final structure. The first algorithm can actually be integrated with the shift reduce parsing to give the recommended actions, whereas the second one directly outputs the final tree. Okay. Now let us see if there are multiple dependency parsing algorithms, or suppose there is a dependency parsing algorithm, then how do we judge its performance? So evaluation of dependency parser. So there are mainly two different metrics that people use. One is unlabeled attachment accuracy, and second one is labeled attachment accuracy. So let us see what they mean, and we start with unlabeled attachment accuracy. So here we count the percentage of words in input that are assigned with a correct head. So we said that there are heads, and so for each edge we'll have a head and a dependent. So we're trying to see, we're considering each word as a dependent and see which head word it is attached to. So for book, again it's a root, and then for me, so it's the actual tree and this is the predicted tree. So okay, let us look from this predicted tree. For book, anyways, it's the root. There will not be any specific head word, or the head word is null. For me, the root is flight. Let me have the pen here. So for the word me, it is attached with flight. And if you look at the left diagram, me is attached with, what is the head word for me? It's book, right? So it's not matching. So for me, it did not match. For the head word is flight, right? The to flight, for the head word is flight. Left hand diagram also, there is the edge. So for the, in both cases, the head word is flight. Then for flight, the head word is me in the right hand side. Left hand side also, we see that for flight, the head word is, for flight. Okay, right hand side for flight, let me see, the head word is book, right? There's an edge from book to flight, so head word is book. Here also it is from flight to book. For through, head word is Houston. Left hand side also for through, it's Houston. So this is correct. Then for Houston, sorry, for through, there is no head word. Yeah, for Houston, there is Houston to through, so head word is through. I think here also it was the same. And book anyways is assigned to null. So we see that out of 6 cases, in 5 cases, the word has been assigned or attached with the correct head. So the score is 5/6. So here, one point to note is that we're just looking at the head word and the dependent word. We are not considering the labels of the edges. So that's why it is called unlabeled attachment accuracy. Now, if we consider the labels as well, edge labels, then we get the labeled attachment accuracy. So for that, percentage of words in input assigned with the correct head and dependency relation. So this thing comes additionally, and dependency relation. So again, let us see. So we saw that for me, there was no match of the with the head. So anyways, will not consider. Among the remaining 5, book is connected to null parent with label root in both the cases. So there is a match. For the, it is connected with flight and the label is determiner. It's matching. So this is correct. Then for flight, it is connected to its head as n subject. For flight, here it is flight sorry, I think I made a mistake here. So let me start from the beginning. For me, there was no match. For the, it's starting with flight, label determiner. So in both cases, it is matching. For flight, it is xcomp connected with book. For flight, is connected with book, but the label is I object. So this one, although the H direction is matching, the label is not matching. Then for through, we have connection with Houston with label as case, matches. And for Houston, it is coming from flight with n mod, coming with flight n mod. So yeah, so here also it's matching. And book, yeah, it matched. It's connected with null with the label root, and the same thing here. So out of 6, in 4 cases we matched. We were able to match with the actual tree. So the label attachment score is 4/6. Okay, so is it clear?
Sir, can you go to the previous slide once? Here this network is trained end to end, or the language, the LSTM language model is trained separately and then the multi-layer perceptrons are put on top of it.
Okay, need to see the paper how they have done. I mean, it's possible to do it, train it end to end, no?
Okay, can you please explain this again? I couldn't quite grasp it, how it would be possible.
Okay. So here the idea is that for the different possible edges, okay. Let me open the paper itself. End-to-end training. This is for the other one, I guess. Mm, yeah. So they want to predict and score. Right. So essentially for each part, they are assigning the score for y. And yeah, and what is y? Y is coming from the set of possible parses. And for each of those possible parses, the final score is the summation or aggregation of the scores for the part. Input sentence S and the corresponding sequence of vectors x1 to n. Look for the highest scoring parse tree y in the space ys of the valid dependency trees over S. So in order to make the search tractable, scoring function is decomposed to the sum of local scores for each part independently. So arc vectored graph, yes. The feature extracted uses the BiLSTM encoding of the head word and the modified word. So feature is what? The RNN representation of the SHM for H for M and right. Okay, now suppose Y is a valid dependency tree. And in that valid dependency tree, there will be certain arcs. Now here, these are the different arcs. Arcs are colored in, arcs are marked in different colors. So the total score for the entire parse tree will be the sum of scores of its edges. And for each edge, how do we find the score? Each edge will have two endpoints. Say, for example, the fox, two endpoints. One endpoint is the other endpoint is fox. We'll get the BiLSTM representation for fox. We'll have the BiLSTM representation for the, and we'll pass both these representations to an MLP. This MLP will output a real number, which is the score for this edge. And the same MLP, same weights will be shared across all these MLPs. Will also give scores for the other possible edges. If we add up those scores, finally we have the total score for this parse tree. Now, if there are some m number of possible parses, we'll compute these m different scores, and then we output the one which has the highest score.
So what is the loss function for training the by LSTM?
Let's see what they have used. The training objective is to set the score function such that the correct tree y is scored above incorrect ones. So it's margin based objective, aiming to maximize the margin between the score of the goal tree y and the highest scoring incorrect tree y prime.
So this is bit like contrastive loss.
Margin loss.
Hmm.
Okay, so the link to the paper is there, so you can go through it. So speed improvement, and since we are talking about many trees, definitely the time complexity will be an issue. So
For every
yeah,
tree, it will be ON scale, right? Because you have to do it for every word pair.
when we talk about a tree, the edges are already defined, so that will be order n. And yeah, but then there are
No,
many
sir, but
trees.
I don't think so. How will it be, or it be order n? Because I need to take a word, I need to find a edge with the second token, third token, fourth token.
So
Then
for a
for the
give, so if they are considering the tree as an input, like for this tree, what are the edges? So now when we say this is a tree, the edges are already defined.
no, the edges are defined, but that's the ground truth, right? Or you are saying that there are certain pre-configured edges only on which we will be uh, training this network, because then it won't work at inference, right? At inference, it's like just a bunch of words.
Hmm. So again, that part also will be there. I think somewhere they mentioned that scoring parse tree y in the space yes of valid dependency parser. Hmm. Graph parser, each dependency arc in a sentence is scored in MLP.
So it's written now, when parsing a sentence, we compute scores for all possible n square arcs and find the best scoring tree using a dynamic programming algorithm.
Right. So yeah, they are constructing the tree. They are not assuming that okay, we are starting with a tree, edges are given, and then find a score. Yeah. So they are checking the possibilities for all in square arcs, and base scoring tree they are finding using dynamic programming. Yeah. So total number of possible trees will be actually large. So 2n factorial by n factorial n plus 1 factorial, like that. Hmm. Okay.
Got it. Yeah.
Okay. So that was the last slide for dependency parsing. So we can actually then go for a break now. Maybe we'll have a 15 minutes break. After that, we'll come back and we'll start with semantic role labeling. Yeah. Okay, so I guess we are back and we can start the next part of our today's lecture. So it will be on semantic role leveling and or semantic parsing rather. Semantic role labeling is one type of semantic parsing. So what is semantic parsing? So if we look at dependency parsing, we're trying to see, okay, how the different words are related to each other. Then semantic parsing tries to give a higher level of understanding of what is contained in the entire sentence. So it's not limited to the relationship between the individual words, but some better idea regarding what is happening in the sentence. So let us look at, let us start with a few examples and then I think it will be clearer. So when we say semantics, actually we deal with meanings, right? Now, if you look at the sentences listed here, we'll see that the sentences are mean the very similar things, but written in different ways. So I'll pause here for a minute, maybe go through the sentences and try to guess their meanings. See, so last week Min broke the window with a hammer. The window was broken with a hammer by Min last week. With a hammer, Min broke the window last week. Last week, the window was broken by Min with a hammer. Min broke the window broke. So thing is that window, there was a window which broke and then it was broken by a person called Min. Uh, so a hammer was used to break the window and it happened last week. So the same thing has been covered in the different sentences. In some cases, some details are missing, but the core concept is there intact in all the sentences. And there are a few sentences where all these pieces of information are present. There are a few where some subsets of these information were present. So this one, say that a similar to this one could be something like yesterday, Christina hit Scott with a baseball. Scott was hit by Christina yesterday with a baseball, and so on. Again, same thing said in different ways. Now, if you look at the individual words like Christina, the role of Christina in each of the different sentences are the same, although the sentences lexical appearances are different. So she is the one who is performing the action. And what is that action? Hit. Hitting is that action. And everywhere also we see that the hitting was done using a baseball, so which is the instrument for that action. And we again see yesterday is when the action had happened. That means the time is yesterday. And Scott was hit and so on. So what we see is same information nuggets, same bit of information, multiple sentences, but they are different. They have different appearances. So if from this you want to get, you are able to get a structure or something kind, yeah, a structure where you mention who is the performer, who is the actor, or what is the thing is being done, then what is the instrument that is being used, then essentially we'll see that all the sentences will actually have the same structure. Now this is what we want to achieve, or something similar to this we want to achieve. So we want to identify the role of each individual phrases, or not that the role of each individual phrases. So the different roles of the phrases which are meaningful. There can sometimes be one or two phrases or words which are left out. That's okay, but the code meaning should be captured using a semantic structure. Now, when people talk about, say, NLDB kind of approaches, right? NLIDB, so natural language interfaces for database. So somebody gives a query in the natural language form, and that gets converted to a corresponding SQL form. So that can also be considered to be one kind of semantic parsing, where your original natural language sentence is given a specific structure, which is the SQL statement without any ambiguity, and then that is executed by the SQL and the database engine. So there also, in order to reach that, we want to identify, we may have to know the semantic roles of each and individual thing, and then from that, the structured query can be created. So these are some examples of semantic role labeling. So here, these are the different semantic roles for the different words present in the, or phrases present in the sentence. So if you look at the parse tree, the constituency parse tree, we see that they are different, right? But that semantic role will be the same. One more example, the police officer detained the suspect at the scene of the crime. So here, who is the person who is performing the action? So the agent of this action is the police officer. And answer to this we can get if we identify the verb like detained, which is the predicate here, and ask the who question to it. So who detained? The police officer detained. Then if we again ask whom did the police officer detain? The answer is the suspect. So it becomes the theme of that. Then if we again ask the question where, then we get the answer, the location at the scene of the crime. So irrespective of how you alter the sentence, keeping the same meaning, the answers to these questions will remain the same. So these are the semantic roles of the words or phrases. So semantic roles help us in determining who did what, to whom, when the action was performed, maybe where the action was performed, and why, sometimes the reasons also, and how. And if we are able to, get these semantic roles right, it can be helpful in various downstream use cases. For example, it can be helpful for question answering. It can also be helpful for constructing knowledge bases. It can also be helpful in many ways for machine translation kind of systems. So if you look at the target sentence and source sentences, the semantic roles for the corresponding phrases in different languages will remain the same, will need to remain the same for a meaningful translation. Even for summarization and so on also, people have seen that the semantic roles, if you're able to identify, it becomes easier to group together different information nuggets from different uh, parts of the input or different sentences, and that can help in uh, the summarization process. Now, my question to you is that, have you seen something similar where we try to address, where we try to identify these kinds of answers from a given sentence? Answers to these questions from a given sentence. Have you seen any cases earlier? So to give you a clue, I think all of us, or most of us rather, have done something similar to it in our school when we were uh, studying language, maybe first language, second language.
So I think it's that reading comprehension type.
Not really. Reading comprehension, the questions can be open-ended also. So here, there is some grammatical constructs, something which has to deal with the grammar and linguistics, where we try to answer these things only.
Active and passive.
Mm, no. Again, this fine-grained information may not be needed there for active and passive. Any other guesses? Okay, so let me give you the answer. So I guess you remember something like vibhakti. Yeah. So karta, karma, karan, sampradhan, apadan, and things like that. So the answer to who is actually the karta, or the person who is performing the act. Uh, yeah. Then what is the object or karma? Often this comes under the dvitiya vibhakti, and then the instrument by which the thing is being performed, how it is being performed. So that is dwara. That thing comes as a karanam or in the dvitiya vibhakti. Then for whom, to whom, so that becomes a sampradhan. Then the point, the location, the place, that is the apadan. Then no, that becomes adhikaran, I guess. That location becomes adhikaran, and possessives are there, some of them are there. So many of these things are actually connected well. Now, although we are studying again now in the context of NLP, now to get fine-grained meanings from different things, but the formal structure for this is already defined in the grammar, and yes, so that thing relates seamlessly with these kinds of structures. But here only the extension would be that we can actually define different kinds of semantic roles. So for these basic kinds of semantic roles, this is the thing, and we can think of some higher level semantic roles and so on. And yeah, there are many data sets for that as well. So yes, semantic roles, if you are able to understand, then it can be helpful in certain other tasks as well. Although recently there is a trend of doing things in end-to-end manner, but still in many of the cases, people have seen that if you have this kind of fine-grained information, this and you feed it to that model as an additional signal, then often they have seen that the model performance becomes better. And at the same time, even many of these end models, when you combine with these kinds of inputs, you may also be able to explain your final decisions better in some sense. So there are linked to a couple of papers on this towards the end of this presentation. So this is one theory. Again, it goes back to connects with the previous slide, whatever we said, but some more examples are there. So agent is the actor or the performer for an action. So musician performed a new piece. Then the patient is the entity which is affected by the action. So it's like that, Samantha hurt her hand. Her hand is the patient here. Not only hand, but her hand will be the patient. And then there could be some instrument by which the action is being performed, like broke the window with a hammer. So the hammer is the instrument. Then there could be some beneficiary, so entity for whom the action is performed. So mother bought ice cream for the children. This is the Chaturthi Vibhakti. Then source, which is the origin of the affected entity. I got the book from my friend. So the source becomes the another role, the destination becomes another role, and so on. So again, as we mentioned earlier, so the task could be like given an input sentence, you if these are the different roles, you identify the different roles. So again, it becomes something like a classification problem. But then what are the classes and all that may depend on from dataset to dataset. That may vary from dataset to dataset. So here there is a list of some thematic roles which is coming from one specific dataset: agent, experiencer, force, theme, result, content, and so on. The definition and examples are there. So right, different datasets will have different thematic roles or semantic roles or role levels. Now there is something called thematic grid or case frame. Again, suppose in the data set, you have the sentences and the roles of different words marked in the sentence. Okay, so in many cases, the agent will be the subject itself. In some cases, the instrument can also be a subject and so on. So the dataset will have these kinds of inputs and the labels for some of the words. Now, then there is something called verb alteration. So when people frame the data sets, they try to cover examples from varied types, so that when we learn certain rules, actions, or algorithms from the data set, that those will be meaningful. That will have higher coverage as well, or generalize well. Will generalize well. So if you look at the example here, Doris gave the book to Carrie, and Doris gave Carrie the book. Meaning is same. The core words are also the same. Appearances are different. So there are some verbs for which the sequence can be altered, and yeah, active to passive voice also, there can be some alterations. So different semantic classes of verbs show this kind of alteration possibility. And there is a data set called VerbNet, which has many such classifications and alterations. So, all right, so VerbNet is one very useful data set that people use for to train semantic role labeling algorithms. Now, if you look at these kinds of thematic roles, it becomes sometimes slightly difficult to annotate and work with that. So for so many different sentences, the labels will be there, but a little more structured way could be, suppose we have, so for some verbs there will be some roles which might be prominent, some verbs for some other roles might be more prominent, and so on. So if we can have something like, for each word or for each sentence, is there a way in which somehow we can unify, or we can have some common sets of roles? So that's where this thing comes in. So there was this data set called prop bank or proposition bank, where the roles, people say, are the most common two roles will be proto agent and proto patient. The definitions will be there in some future slide. Just confirm that. Yeah, so proto agent and their examples are also there. Fine. So let me move on to this one. So in this data set called prop bank, certain phrases are marked as proto agent. Proto agent are the ones who are performing the action. Okay, so direct or major involvement in performing the action, and this is the person or entity or object that is causing an event or change of state in another participant. So the person or entity or object that is performing the action, which could be the subject in most of the cases, so that becomes the proto agent. Proto patient is again the person or entity or object or the thing that is undergoing some change of state, or that is actually absorbing or getting modified due to the action which is performed in the verb. This is causally affected by another participant, which is the proto agent. Then there can be some other kinds of arguments also. The next slide, where it has more examples, will make it clearer. Suppose there is a verb called agree. Now this verb agree can have many different senses or meanings. One specific group of senses is marked there in prop bank as agree 01. Now for this meaning of the verb agree, there are many sentences where parts of the sentence or the fragments of the sentences are marked as arg0, arg1, arg2, arg3, and things like that. Arg0 means what? Arg0 means the proto agent, the person who is directly performing the action. In this example, the group agreed it would not make an offer. So who is agreeing to the group? So this becomes the argument 0 or the proto agent. And what do they agree upon? They agree upon the fact that they would not make an offer. So this becomes the proposition. Then for the next example, usually John agrees with Mary on everything. So again, the verb is agree, which is the main action being performed in the thing. Who agrees? John. So John is agreeing. So this becomes the main actor or the proto agent. And does he always? When does he agree? Usually. Now these are temporal kind of argument. So this is another level. R2. Sorry, this is another level. Argam temporary. Then agrees with whom? That is R2. Other entity agreeing. On what? On everything. So this is arg1. Let us look at one more example from the dataset. Fall. Now the word fall can also have many meanings. So here we are talking about the first word sense of the word fall. So that is denoted as fall.01. Now there again a couple of examples are there. And in these examples, what are the different arguments that we can expect? So actually these all different types of arguments will be valid for this interpretation of the word fall. So argument 1 will be the logical subject or the patient or the thing that will fall. Argument 2 will be the extent or the amount by which it fell. For example, the average junk bond fell by 4.2%. So although the word here is fell, the root word for that is fall. So it will come under this category. And what fell? The average junk bond. Now the subject or the thing falling is argument 1. So this becomes the argument 1. And by what amount? 4.2%. So this is the extent or amount fallen. Now this becomes argument 2. Then sales fell to $25 million from $27 million. So again, the sense is of this sense of fall, and the thing that is falling is sales, which is argument 1. And this is the starting location or starting position or start point for the fall, 27 million. So this is arg3, and this one, the final position or the end position, end point, $25 million. So this is arg4. So what do we see here? For each verb, different senses are marked, identified, and for each of the sentences, these kinds of things, arg0, arg1, arg2, what will be their meanings? Those are listed, and there are some examples where the input sentences are annotated with these kinds of labels. So although this is quite helpful, we also see some issues with this. What are the issues? The issue is that we need to identify the sense of the so we may need to identify the sense of the verb. And also if you look at arg0, 1, 2, sometimes their meanings are actually changing across different verb senses. So some other example would be like increase.01, where again another sense of one sense of the word increase, where it grow up incrementally. And the labels which are defined and examples are given here are the causer of increase, the thing that is increasing, and so on. So arg0 is causing an event to change, and arg1 is the thing that is experiencing the change, and there can be some things by which there is no arg0, and so on. Now, although this prop bank is used quite a lot in this one, in semantic role labeling or this kind of thematic roles, now the problem that becomes is that listing these things explicitly for different senses, then having some examples and all that becomes slightly tedious while working with the data. So we can think of many algorithms, but again, we need to see how with the available data set we can, this algorithm works in that, so that context, right? So data set context we should not forget. So this thing creates a problem. On the other hand, if you see that there are certain words for which some of these arguments or meanings can actually be shared. Say increase, then if we have decrease, then many of these things could be shared. Fall, if we have rise, we can have some of these. And also some other synonyms of fall in this current sense, they also may have the similar kinds of things. So listing all these things separately under all these word senses and so on becomes slightly problematic. So yeah. Okay. So then people try to construct some other kinds of data sets. And the next one here would be FrameNet. So before moving to FrameNet, yeah, so we said that arg0, 1, 2, 3, 4 are there, and there are some other commonly used arguments like temporal information, location information, direction information, other things can also be defined inside the prop bank. Next, people came up with the concept of FrameNet, where so it came up based on the observation that if you look at certain verbs and the context in which the verb appears, the different other words which are there in the context, you often see lots of similarities in the context, lot of common terms that are being used in the context. Say, for example, different verbs could mean the same thing or similar thing, or they may be used under to express similar kinds of actions. So if we consider the following sets of words like reservation, flight, seat, book, ticket. So these are nouns, meals, plane, price, and the verbs that appear along with this context, you will see, there are some commonalities with those verbs. So some examples are here, that advance, climb, decline, decrease, diminish, drop, jump, gain, grow, reach, rise, shift, all that. So the words which are there, the nouns, different nouns which are there in the context of these words, often you see that these things will tend to reappear. So we can say that these words are used in a common sense background information or context. And this background knowledge is referred to as frame. So there is an example of a frame in this slide. A frame will consist of words. So, so suppose this frame is called hit target. Okay, and the different verbs which can participate in this frame could be hit, pick off, shoot. So these different words can evoke the frame. And all these words together may have some of these commonly used additional informations, which are called the frame elements. And these things would be the semantic roles. Okay, so earlier what we were doing in prop bank, sets of roles for each verb separately, each sense of a verb separately. Here we are trying to group together some of the information present there. So the same word can have different senses. So here we are actually combining all the things here. So some of the sense information, fine-grained sense informations may be lost, but many different words which are used in the similar kinds of senses, we are able to group them together. So some of the semantic roles will actually core, and we expect them to be present for each of the different frame elements. Sorry, each of the different verbs or lexical units for the frame, and there could be some other things which are optional. So again, in this example, Christina hit Scott with a baseball yesterday. So since the word hit is present, we'll look at this frame. Okay, and there's some kind of semantic roles we may want to identify. Okay, so okay, semantic roles are helpful for various tasks, helps in making simple inferences that might be difficult to make from the lexical string of words or even from the parse tree. So examples are question answering, like who did this, where did it happen, when was this done, and so on. And the answer to who typically would be the agents, answer to what would typically be the patients, how and with what instruments and things like that. In machine translation generation also, semantic roles are usually expressed using particular distinct syntactic constructions in different languages. So source language, the sentence in source language, the sentence in target language. If you look at the roles of the different parallel words in them, they should match. So that's when the translation will be a valid translation. So now talking about the task, the action. So the predicate is essentially a verb for which we want to identify the semantic roles. So the task of finding the semantic roles of each argument of each predicate in a sentence. And then again, as we said, these are commonly designed as machine learning tasks. And depending on the underlying data set, what labels are present in the data set, the algorithms may vary slightly. So yeah, so you can't blame the program for being unable to identify it. So essentially, these labels will come from the FrameNet, and these labels are coming from the prop bank. Labels are different, and yeah, if we want to design an algorithm for based on FrameNet data, it will be different. For this, it will be different. I mean, that entire algorithm may not be different. Suppose somebody may use naive Bayes or say support vector machine or something, but number of classes and then the training procedure, the training that model will be different. So some example rules: change position on a scale frame. So we saw that example of fall, increase, and so on. Yeah. So the core rules will be this, and some non-core rules could be this. So again, this is coming from a frame, and there can be many words which are part of this frame, like increase, decrease, decline, rise, and so on. So semantic role labeling often is performed in multiple stages. In the first part, there is often some pruning is done. So instead of trying to assign, some a semantic role with the entire sentence, so people have experimented and said that okay, if you first cut, identify the words or phrases that may have a semantic role, and then you identify what kind of semantic roles could be there. So that could that helps in boosting the performance as opposed to having one single algorithm. So typically, if you look at large sentences with lots of information, background information, and context, typically only a small number of constituents in a sentence will be arguments for a given predicate. So yes, many systems use simple heuristics to prune unlikely constituents. Then binary classification could be done for each node as an argument to be labeled or none. So then whatever is remaining, on top of that also one can design an algorithm to see that whether we need this thing in the final classification or not. Sometimes these two parts can also be merged, and then this classification could be like one-to-one mapping of which role we should assign to this phrase. So yeah. So here's one example where people, it is from, it's from paper. The hyperlink is not mentioned here. So here the parse tree is used to identify features for doing the semantic role labeling task. The San Francisco Examiner issued a special edition around noon yesterday. Okay, so this is a sentence from prop bank, and the different argument labels from prop bank are shown here. So the San Francisco Examiner is marked as argument 0. Then issued is the verb, which is the target, which is actually the predicate in the context of this verb, we want to see the roles of different words. Then this is arg1. According to the level, this is around noon yesterday is a temporal argument. So this is the parse tree that we have obtained. And what is our goal? We want to identify the role of the constituent, the San Francisco Examiner, in this sentence. So the algorithm that was proposed in the paper, so it tried to look at these different features. So this is the constituent, the San Francisco Examiner, for which we want to find out the role. So the head word of this constituent is examiner, and the part of speech for that head word is NNP, nominal noun phrase, and it is an inactive voice. Okay, and then the subcategorization of the predicate. Subcategorization of the predicate is VP, VPD, NP, PP. VP, VPD, NP, PP. So this one, the predicate is here in the tree. It is part of the VP, right? So what is the subcategorization? What is the rule? What is the grammar rule here? VP to VPD, NP, PPT, MP, or simply PP. So this is the subcategorization. The named entity of the constituent, this one is organization. The first and last words of the constituent, first word is the, last word is examiner, and linear position of clause with respect to the predicate. So the predicate is here and the constituent is here. So it is appearing before the predicate in the original sentence. So this becomes another thing. And what is the path to the what is the path connecting the constituent to the predicate? It is NP, this one. From NP we are going up to subject. U means up to subject. From subject we are going down to VP, right? Subject to down to VP, and from there VP down to VBD. Right? So this is the path from the constituent to the predicate. Now these things can actually be appropriately be vectorized, and that thing can be given as input, and then the target could be the role that has been assigned in the data set. So this is the, then once we have everything in this format, one can define some kind of, or one can use some kind of classification algorithm or come up with own classification algorithm with these sets of features. Now one very crucial thing to note here is that often although these algorithms, these features are good enough, many a times when there are some results which are given, based on these we can actually reason why this answer was given, so on. One thing is that many of these actually use other underlying NLP algorithms. So so this one, head word of the constituent, examiner. So this one can be obtained from the dependency parse. Head word pause in NP. So this one is coming from the constituency parsing. Now voice of the clause active. Again, this is a classification algorithm that will say whether it's active or passive. Then subcategorization of the predicate. This we can get from the constituency parse. Named entity type of the constituent. So here we are using any NER algorithm. First and last word, this is straightforward. Linear position, this is also straightforward. And this path again coming from the constituency parse. So when people try to design toolkits or for NLP kinds of applications, so all these very small algorithms that we see here are designed as low-level algorithms which fuel the performance of the many higher level or closer to application kind of tasks. So then again, there are many neural architectures also people have proposed, or neural algorithms people have proposed for performing these kinds of tasks, where so this is again from a paper, deep semantic role labeling. So here, so this is the sentence which is given. The cats love hats, and love is the predicate here. Okay, so inside this sentence only we'll try to identify what are the roles for different things, and here love is the predicate, but this one with this, so this is explicitly marking. I'm not very sure how they wanted to, yeah, maybe they wanted to explicitly mark the word that is there as the predicate so that it's BERT, so self attentions can be computed, and it will give a lot of insight. But you see that for the next level, after the BERT representations are given, representation of this love is not used. So essentially, for this we are not going to assign any label. Yeah, for this additional thing, but labels will be assigned to this one. So this is BERT. BERT will give the representation of each of the words. So they have used the representation of CLS and separator token also. And these things, with this BERT output, they also add something like whether it's predicate or not, 0, 0, 0, and love is the predicate. So there is 1 here and that. And from this BERT output, they have used a by LSTM. After BERT, by LSTM is not very common. Okay, again, this example is there in the book. I just took it. Yeah. So then they concatenate the different signals that they're getting from by LSTM, the signals that they're getting from BERT, and also, yeah, and then these things are coming, and then now they want to assign the labels. Here again, since it's something of a some sort of sequence labeling task, here also this BIO encoding is used. So it's the beginning of arg0, and this one is inside arg0, and then we have bpred. So beginning of the prediction, so predicate. So this one is actually used to indicate in this part what are the different things that we should combine. So the and from this predicate, both these things are coming together, and then the MLP is deciding what is the role of this word in the context of this predicate. Similarly here also. So with BIO encoding, so this is beginning of argument 0, this inside argument 0. So these two we can combine. Next is bpred. So the argument 0 stops here. So the cats is the argument 0. Love is the predicate, beginning of predicate only. And then hats is beginning of argument 1. So, all right. So this is one more algorithm from 2017 for, yeah, semantic role labeling. Any questions till this point? So these are some simple algorithms that I have listed down. So there are many sophisticated algorithms, many different algorithms which are designed from different angles. Even those things are there. So here we have listed down some of those references for a reference. And as you can see, quite a few of them are very recent also. So the effect of syntactic representation on semantic role labeling. So this syntactic representation can come from the parse trees. Then this is something where they show that the syntax for semantic role labeling, how the syntax could be useful, or what are the cases in which these are not being useful. So this is a study on that thing. Next one, span-based semantic role labeling with argument pruning and second order inference. So yeah, so pruning technique is used inside. And next one is transition based. So that transition based parsers are actually quite commonly used in NLP, and transition based semantic role labeling with pointer networks in a very recent work. And we said right that the semantic roles, if they are identified correctly, then they can also lead to better performance in many downstream applications. So here, people use plagiarism detection, and sorry, they do plagiarism detection, and on that, for that problem they use semantic role labeling. Here, semantic role labeling tools for biomedical question answering. Yes, question answering definitely is a very direct application for semantic role labeling. Then the detection of product comparisons. Uh, so how far does an out-of-box semantic role labeling system take you? So yeah, product review. Then semantic role labeling for sentiment inference, uh, and semantic role labeling for improving neural machine translation. So applications are quite a lot. So again, these are some pointers or references. So depending on your interest, actually, you can go through some of them. Any questions? Okay, so apparently there are no questions here. We will start the next topic, which is on co-reference resolution.